Hello and welcome to the new session of the Molecular Point Group. This is referred as the summary of the shape. I'm your instructor, Dr. Saurabh Bhaktibod again. A summary of the shape corresponding to different point group is presented before you. The group to which a molecule belongs can often be identified from the diagram or the figures without actually going through the entire procedure, the formal procedure. And for that reason, we have chalked out, we have made certain pre-made structures, and by observing and correlating these structures, the point group can often be assigned. Now just look at this canvas before you. There is a CN point group with various CN symmetries. These are molecules with DN symmetry. These are typically CNV symmetries. Here it is CNH symmetry. Look at the DNH, very popular DNH symmetry. DND symmetries and S2N symmetries. So most of the symmetries have been covered so that you can identify the molecular point group without actually using a formal procedure. So let's begin the journey. We'll begin with the first thing, that is CN. Look at the shapes of the CN geometry. Had it been C2, it would look like something this. C3 would be something like this. C4 would be this, C5 and C6 symmetries. So you just notice the angular parts. So these are the third dimension of the structures. So they are making like pyramids and all that. And therefore it's quite easy to assign, except the fact that they have got additional extra bonds here and there. So such symmetries are very common. And if you wish to know about these symmetries, if you just start with this abnormal something, that is C1 is not included here. C1 is the case where there is no symmetry at all. However, the hydrogen peroxide configuration has been given as an H2O2 symmetry. So you just assign the H2O2 symmetry C2. So you'll find that it is something like the H2O2 symmetry. You have to go back, see the structure, correlate the structure, and you get this. For example, this complex of cobalt has been given, and the triphenyl phosphine has also been assigned as C3 symmetry. So the structural correlation often helps in making the predictions of molecular point group. The most common of the structures are the CNV structures. The CNV structures are typically the structures which have a third dimension, and normally we encounter various molecules which have this kind of structures. What you notice here is that they have a third dimension coming out of the plane here, and therefore this is assigned a C2V symmetry. Look, water is given a C2V symmetry, ammonia is given a C3V, C4V, as we have studied about the Taj Mahal symmetry, that is C4V. Similarly, had it been C5V, it would look like something this. Had it been C6V, and finally had it been C infinity V, it would appear like a cone. That's why in my earlier presentation, I have given that the ice cream cone as an example for C infinity V symmetry. So correlation techniques would work. Just look at this: water C2V, the ammonia, the pyramidal C3V, BRF5, C4V, and C infinity V, that is HCl kind of system. So it's that easy to just correlate the structure and put a molecular point group to that. DNS symmetries are again another kind of symmetries that is available for the flat molecules. And see the structures for D2H, D3H, D4H, D5H, D6H, and D infinity H. These structures are the structures, if you just simply correlate these structures, you will find that these are the flat systems, and most of them, in fact, all of them should have molecular plane or the horizontal plane of reflection. So you just a rectangle or a triangle or a square or a hexagon. So these kind of structures make a DNS symmetry. You just notice some structures like D2H, a C double bond, C bond, ethene, or say boron trifluoride, D3H, or say square planar complex of platinum, tetrachloroplatinate ion, a D4H symmetry, and say benzene, a D6H symmetry. So what is common in all these structures? They're all flat, and therefore assignment of point group is very simple to these structures. So just look at the D5H and D6H symmetry in eclipsed conformation of ferrocene and dibenzene chromium. You'll also find that they're having the D5H and D6H symmetries, and similarly D infinity H, because this is a cylindrical kind of system that would come out, that would have been assigned a linear molecule, and we assign a D infinity H symmetry. So assigning a D symmetry, DNH symmetry, is very not only popular but very easier to understand and to work out. Connected to DNH, we would like to talk about the DND symmetries. Now DND symmetries like D2D, D3D that you can see here, or D4D, or D5D, or D6D, these structures, if you have noticed it, and these structures are actually the staggered conformations of various molecules. And therefore, looking to these structures, the assignment would be easier. Like, allene molecule. Allene molecule has been assigned as a D2D. Now, D5D eclipsed conformation, that is the D5D structure is there. And similarly, a D6D structure is there with the diamond chromium situation. In all such cases, there is a very peculiar staggered conformation that has been observed. If we talk about CNH kind of systems, CNH are typical of D2H, but the fact is that they have got an extra curves that make them different from the routine geometry. Like, the structures like C2H, where we have the dichloro 1,2-dichloroethene, or say N2F2 molecule which has a C2H symmetry. And similarly, if you talk about H3BO3, that also have been given as a C3H symmetry. So assigning these symmetries is, from their structural point of view, is not very difficult indeed. And similarly, there are two odd situations. One is a DN situation. There are not many molecules which have this configuration, but if such configurations are there, D2, D3, D4, D5 and D6, they would have this kind of geometries, this kind of shapes, and therefore the assigning the point group would be relatively simpler by analogy. Like, tris ethylene diamine cobalt 3 cation has been assigned as a D3 point group. You just notice the structure here, and similarly, you just notice the D6 structure of the ethane molecule. Finally speaking, we talk about S2N symmetry. S2N symmetry has typically, it starts with S4 because S2 does not exist, which is equivalent to I only. So S4, S6 and S8 geometries are very common. And if you just watch and notice that this molecule, that is the ethane staggered form, gauge form, has been assigned as a S6 symmetry. So assigning symmetries on the basis of correlation of various geometries is a relatively easier task, and therefore I suppose that this is interesting to go without actually adopting the formal procedure. Thanks for watching. Thank you.